Let's look at some more optimization problems involving this approach that I'm recommending, but please promise me you're not about just memorizing how to do one particular problem, then another particular problem, or whatever. All you have to do is learn to be flexible and see the beauty of the big approach, and then everything else kind of takes care of itself if you just look at it from that perspective. So you don't have to spend forever memorizing and hoping to prepare for just the right questions on a test. So here we go. This is the big idea. Use calculus to optimize a function. Step one, what quantity we're trying to maximize or minimize. Step two, you're going to draw a diagram and create a function. At the same time, use as many different variables as you want to. I think that's probably the key. Don't try to go right to a final function of one variable. You're likely to make a goofy mistake. So make step three when you bring the function down to one variable using the extra information from the problem. And then step four is to use calculus, set the first derivative equal to 0, and you're on your way. So again, a big key to this situation is be okay writing a function using more than one variable, like the volume function as a function of 3 different dimensions or 3 different variables. Okay, so we have an open top rectangular box with square ends having a volume of 8,000 feet square cubed, and it's to be constructed at a cost of $4 per square foot for the base and then $1 a square foot for the other sides. Find the dimensions of the least expensive box and give the answer to the nearest hundredth. So we look at all this information. There's a lot out there, but the first thing we hone in on, step one, what are we trying to minimize and maximize? We're trying to figure out the least expensive box. So this is going to be a cost function that involves us figuring out what the dimensions are in order to get to minimize the cost of creating the box. So we have it. We're going to minimize a cost function. Step two. Let's draw a diagram and let's come up with a cost function for that diagram. And here it is. We were told that the two ends were square, so we'll make the ends square, and then a second dimension will be, or a second value of a dimension will be y. So that's all we need as far as the lengths of each of the sides goes. But then we need this cost function, and the information to us, if we recall, was that it's $4 a square foot for the base and then $1 a square foot for all the other sides. So the base has dimensions, it's a rectangle of x times y. So the base will be x times y, and that's $4 per square foot. So that's how we come up with the cost of making the base. Now we have two sides, left to right, that are square. They're both x by x as far as their area goes, and they only cost $1 per square foot. So it's $1 times x squared, but there's 2 of them. So is that okay if we just say 2 of them at $1 each would be 2x squared? So we'll leave it that way. Then finally we have the front side and the back side. They're both x times y as far as the area goes, and they both cost $1 a square foot. So we have 2 sides that are both xy square footage. So we have plus 2xy. There it is. There's our cost function as a function of x and y. We didn't try to come up with a cost function just in terms of x on the first try. Too tedious. But that ain't bad. That's doable. We can handle that. It's a cost function. So we put all that together, utilizing the drawing, the diagram, and that. So then what we want to do now is say, okay, now can we rewrite this where it's the cost function of just x? So now the third step becomes, let's rewrite this guy as a function of just x. So we want a cost function involving x, but what we're going to have to do then is we're going to have to try to find a way to represent y in terms of x. So we go back to the original problem. Where's that information? Well, that's right here. The total volume of the box is going to be 8,000 feet cubed. So if we look at this, we say, oh, okay, now we go to that information about volume. We know how to get volume of the box. It's the base times it's the 3 dimensions, base, height, on depth, whatever you call it, but it's y times x times x. So our volume as a function of xy is going to be x squared y. And we know that that volume, is this, okay, that volume is going to be 8,000 cubic feet. So if we solve for y in terms of x, this information regarding volume will help us do that. So we divide both sides by x squared, and here it is. We have now represented the value of y in terms of x by using the other information in the problem. So now what we can do is we say, well, everywhere we see y, we can replace it with something that's equivalent. So we're going to go up here, and we see that wherever we see y, we can replace it with something equivalent. And by the way, I guess I should have gone up here, and before I went any further, I could have said that this cost function is a function of x and y. If I combine the two like terms, would be 6xy plus 2x squared. I don't care if we're writing things with the quadratic term before this, it's no big deal. Okay, so now we're going to write this as a function of x, and where we see the y, we're going to replace it with something that is equivalent to y just in terms of x. So, let's drop, well, don't even do that, bring it back. So we just drop this guy down a little bit. So here we go. The cost function as a function of just x is going to be 6 times x times this guy, because this is y, plus 2x squared. Let's just clean that up a little bit and we're good to go. So the cost function is just a function of x. That x cancels with one of those x's. Just be left with an x in the denominator, and 6 times 8,000 is going to give us 48,000, and then plus the 2x squared. So we have the first 3 steps done. I think these are the toughest parts of the problem. We now have a cost function just in terms of x. So here we go. Now that we have this cost function, we can rewrite it more easily so that we can differentiate. So we'll write it as x to the negative 1. And then let's take the first derivative. Ding, boom. And if we keep doing the algebra, hopefully you can follow all that. We end up with that right there. Just again, get everything, get this negative over to the right side, so 4x equals to that, and just isolate the variable. So x equals 22.8943. I didn't pick nice easy numbers, just because whatever, okay, just pick the numbers out of my head. So anyway, so we got this, and that's why I said in the beginning, we'll just round this off to nearest 10th when we're done. But hey, once we have x, we need the dimensions of the rest of this thing, so let's go back up here. And we remember that y was defined in terms of x as being 8,000 divided by x squared. So if we just put that value in for x and square it, we'll get this for y. Rounding off to the nearest hundredth place, we say there we go. Those would be the dimensions of that box that would minimize the cost. So not too bad. So here we go. We have other types of problems using this effective approach. And so the big idea is to understand the approach. Want to find what it is that we're trying to maximize or minimize. And then a diagram and the objective function at the same time, but use more than one variable. It just makes it easier to come up with that function at the beginning. Then go to step 3, rewrite the objective function with just one variable using the extra information from the problem. Set the first derivative equal to 0 and check the domain. So we do a couple of problems super fast. We got, hey, determine the max product of 2 integers whose sum is 12. Oh, what are we trying to maximize? We're trying to maximize the product. Oh, well, the product is what you get when you multiply 2 numbers together. So that's the product. And then, so that's it. We're just going to try to maximize the profit function of x and y, being x times y. Then we go to step 3. We pull out this information. Aha! That the 2 numbers, their sum, whatever, the 2 numbers, their sum is going to be 12. So that means if the 2 numbers add up to 12, then it must be that y equals 12 minus x. You just go back up here where you see the y, replace it by 12 minus x. Now you have the objective function in just one variable. Off you go, it's the same old stuff. And then likewise, what if we had one of these problems that says we want cylindrical cans that have volumes of 180 pi, and we want the radius, we want to find the radius requiring the least material. So we say, aha, the least material. We're trying to minimize the surface area, all right, the material that it takes to make this. But then maybe the problem with this cylinder is how would you find the surface area? I don't know, I just came up with something off the top of my head, and I'm thinking, haha, Oh snap, when you make a cylinder, look at that. You just think about the side of it as cutting down the side and it becomes a rectangle. All right, so basically you just have a rectangle and the length of it's going to be the circumference of the bottom circle. After you put it back together, there'd be a base that would be a circle, and then you'd have this rectangle that those two surfaces together would make the surface area of a cylinder. So just think things through. You don't have to memorize every exact type of problem. You just have to look at the big picture and then carefully, step by step, apply it to each situation. So good luck.